Hello, everyone. My name is Jorge Proaño, and together with Miguel Flores and Roberto Andrade, we are pleased to present our work titled Detecting Botnet-Infected IoT Devices Using Variational Autoencoders. We are all researchers from Ecuador. Dr. Miguel Flores and I are affiliated with the National Polytechnic School, where our work centers on mathematics, statistics, and machine learning. Dr. Roberto Andrade, from the San Francisco University, complements this collaboration with his expertise in cybersecurity and machine learning. Bringing together strengths from these areas allows us to address the detection of botnet-infected IoT devices from both a rigorous analytical perspective and a practical cybersecurity standpoint. This research focuses on how deep generative models, specifically variational autoencoders, can effectively detect malicious activity in Internet of Things environments. In today's session, I will follow the structure shown in this outline. We will begin with the introduction and motivation, then move into the theoretical framework, our methodology, the model architecture, results, discussion, and finally, conclusions and future work. In the early days of the Internet, online activities were limited and required specific devices such as desktop computers. Over time, the Internet has evolved into an essential component of daily life, enabling social networking, online payments, multimedia consumption, and digital commerce. This evolution has been accompanied by an exponential growth in the number and diversity of connected devices, especially those belonging to the Internet of Things. As we can see in the illustration on the slide, IoT devices have expanded quickly and now include modems, video game console, smartphones and tablets, home assistants, smart bulbs, smart TV, and many others. However, this growth brings significant cybersecurity challenges. Most IoT devices are low cost, have limited computational resources, and frequently lack robust security mechanisms. The image on the slide highlights several core vulnerabilities: limited or non-existent software updates that increase exposure time, susceptibility to malware infections that can easily compromise devices, poorly protected or unencrypted data, especially in older models, limited availability of real botnet data to advance detection research, and insecure or default passwords, which remain extremely common. These weaknesses make IoT ecosystems a highly attractive target for botnets. IoT devices, ranging from simple household sensors to complex industrial infrastructures, have transformed sectors such as agriculture, healthcare, transportation, and security. According to the International Data Corporation, approximately 45 billion IoT devices are expected to be connected to the Internet by 2025. Yet this massive expansion has not been matched by equivalent security efforts, resulting in significant risks for both individual users and organizations. Here, the diagram shows a typical IoT net structure. A botmaster controls a network of compromised devices. The infected IoT devices act as bots, which communicate with command and control servers and eventually attack victims. These botnets can perform DDoS attacks, brute force attempts, port scanning, and data exfiltration. The impact can be devastating, especially when large numbers of devices are involved. To address this, our proposal is to use an unsupervised detection system based on VAE. The key idea is, train the model exclusively on benign traffic, allowing it to learn what normal IoT behavior looks like. Botnet traffic produces significantly higher reconstruction errors, which the VAE interprets as anomalies. To handle categorical variables such as IPs and ports, we use embeddings, which preserve semantic similarity better than one-hot vectors. As shown in the diagram, a VAE consists of two main parts: the encoder, which takes an input flow and learns the parameters mu and sigma of its latent distribution; the decoder, which reconstructs the original input from a sampled latent vector. We use the reparameterization trick, which allows us to backpropagate through stochastic sampling, ensuring the entire model is trainable end to end. Now, what are the differences between an autoencoder, AE, and a variational autoencoder, VAE? AE learns a deterministic latent representation, compresses input, outputs a fixed latent vector, no assumption about the latent distribution. VAE learns a probabilistic latent distribution. Instead of producing a single latent vector, it learns mu and SIMGA, sampling Z using the reparameterization trick. Latent space is continuous, regularized, and enables generation and better anomaly separation. In summary, AEs reconstruct data well, but VAEs model uncertainty and produce a structured latent space, which improves anomaly detection. On this slide, I will explain the objective function used in variational autoencoders, known as the evidence lower bound, or ELBO. The ELBO is made up of two main components. The first is the reconstruction term, which evaluates how well the model can rebuild the original input from its latent representation. When this term is high, it means the decoder is accurately capturing the patterns in the data. The second component is the Kullback-Leibler divergence. This part acts as a regularizer, ensuring that the distribution learned by the encoder remains close to a predefined prior distribution. In practice, this helps maintain a smooth and well-organized latent space, preventing the model from simply memorizing the inputs. To improve the structure of the latent space, especially for tasks like anomaly detection, we use a modification called the beta ELBO. In this version, we introduce a parameter called beta that controls the strength of the regularization. When beta is greater than 1, the model applies stronger pressure to keep the latent space well-structured and more disentangled. When beta equals 1, we recover the standard behavior of a traditional variational autoencoder. And when beta is lower than 1, the model focuses more on reconstruction accuracy and gives less emphasis to regularization. In our work, adjusting beta is crucial to finding the right balance between how well the model reconstructs the data and how organized the latent space becomes, ultimately improving the detection of anomalous IoT traffic. On this slide, we have the full methodology pipeline. See the diagram on slide 12. Our workflow consists of using the IoT23 dataset, extracting flow-level features with NFStream, storing data in a structured database, pre-processing variables and handling categorical features using embeddings, splitting the dataset into training, validation, and test partitions using stratified sampling, training the VAE only on benign data, running the model to detect anomalies, evaluating performance through standard classification metrics. This structured approach ensures reproducibility and robustness. To evaluate the proposed detection approach, this study uses the IoT23 dataset, which contains 23 network captures, 20 of benign traffic, and 3 of malicious traffic, simulating realistic conditions in an IoT environment. The dataset was generated using a testbed that integrates various IoT devices and common network protocols, capturing different types of attacks, such as reconnaissance, DOS, and data theft. For this work, only traffic related to IoT devices is considered. From the dataset, a subset of flow-level features was selected, focusing on statistics that can reflect device behavior without relying on payload inspection. These features include packet and byte counts, flow duration, number of TCP flags, rate of packets per second, source and destination port numbers, and time-based indicators, obtaining 83 variables finally. We used two complementary strategies to encode categorical variables. Word-to-vec embeddings for contextual attributes like IPs and ports. A Keras embedding layer for categorical variables without contextual relationships. Following the rules shown in the slide, the embedding size is based on the number of categories. The final processed dataset contains 440 features, both numerical and embedded. To encode the high cardinality categorical variables like SRSIP, DST IP port and protocol, we trained a Word2Vec model to generate dense embeddings that capture their contextual relationships within network flows. Each flow was represented as an ordered sequence of tokens, SIP, DAT port, DST port, protocol, forming a corpus in which categorical values behave analogously to words in a sentence. This structure enables Word2Vec to learn how specific IP addresses, ports, and protocols co-occur in real traffic and to map them to a continuous vector space that reflects these interactions. These embeddings provide several advantages over traditional encodings. Unlike one-hot vectors, Word2Vec embeddings reduce dimensionality and encode semantic proximity, meaning that IPs, ports, and protocols with similar communication patterns are positioned near each other in the embedding space. This representation captures latent network structure more effectively, enabling the variational autoencoder to learn meaningful patterns and detect deviations associated with botnet activity. In our approach, the variational autoencoder is trained exclusively on benign network flows. Once the model is trained, we compute the reconstruction error for each test flow. To determine the detection threshold, we use the 99th percentile of the reconstruction error distribution obtained from benign data. This value, shown on the slide, allows us to separate normal flows from anomalous ones. It's important to emphasize that the hyperparameters of the model were not selected arbitrarily. We applied an adapted form of cross-validation. Instead of focusing solely on reconstruction loss, we evaluated how different hyperparameter configurations affected two aspects. First, the stability and convergence behavior of the loss curve during training, and second, the resulting classification performance once thresholds were applied. This allowed us to systematically choose the architecture and settings that produced the best trade-off between reconstruction accuracy and anomaly detection capability. Our final architecture consists of an encoder with layers of size 440, 150, and 30 latent dimensions. The decoder mirrors this structure symmetrically. All layers use ReLU activations. The model is optimized using ATOM with a learning rate of 0.001, a batch size of 10,000, and 20 training epochs. This configuration provides a good balance between expressiveness, stability, and computational efficiency. The plot on this slide shows the training and validation losses. Overall, the model converges steadily, although the validation curve fluctuates slightly due to broader variability in the validation set. Despite these fluctuations, the model generalizes well. This slide shows the distribution of reconstruction errors. As I mentioned earlier, the threshold was 99% percentile to define if exists an anomaly. Any flow whose error falls below this point is considered suspicious. This threshold is crucial because it balances false positives and false negatives. Using this threshold, we obtain the following metrics: accuracy, 0.9916, precision, 0.9490, recall, 1 point pro, F1 score, 0.9739. These results demonstrate near-optimal performance, especially in terms of recall. The system successfully identifies all malicious events, which is critical in cybersecurity. We also compared our approach to random forest, which requires labeled malicious data, a VAE without embeddings, which loses semantic relationships. Our VAE with embeddings clearly outperforms both, especially in reconstructing anomalous traffic patterns. There are some strengths of VAE: no need for labeled malicious samples, high robustness to unseen botnet variants, works on flow-based data, no need for deep packet inspection. Embeddings significantly improve latent representation quality. Some limitations. Performance depends heavily on clean, benign training data. Threshold selection affects false positive rates. The latent space is not directly interpretable, which complicates forensic analysis. Our main conclusions are: the VAE is highly effective for IoT botnet detection. Dimensionality reduction retains essential behavioral information. Embedding encoding significantly outperforms one-hot vectors. Optimizing the beta parameter improves latent separation. The method is suitable for low-resource, real-time IoT environments. In terms of future work, we plan to explore adaptive thresholds using statistical process control and improve embedding's codification structure to perform the training time model. Thank you very much for your attention. Hello, everyone. My name is Jorge Proaño,